Uh, Good morning. So my talk will be on wood quality and its effect on electrical properties of wood. So basically, because the ERT principle, as one audience also studies the basic principle, basically it measures the way the wood resist or conduct electricity inside the wood, and what are the parameters that affect the electrical properties of wood. So my talk will be confined to the direct DC electrical properties. And before moving forward, just because I'm not a physicist, but just to mention what is the electrical resistance. This is it is nothing but the amount of opposition that current will experience to its flow when moving through a material. When there is a potential difference, and how much current that passes and how much gets absorbed, attenuated. So basically, the electrical resistance, the equation tells it is the ratio of voltage divided by the current, and it is measured in rho, and sorry, ohm, and the resistivity, related to the resistance, and resistivity is the property of the material, and it is represented as uh, it is controlled by the cross section of the material as well as the length of the material. So if you see resistivity and resistance, they both are related if the cross section and length are same. So for instance, if A is unit cross sectional area and the length of the material, or maybe the wood, if it is unit 1, then rho, that is resistivity, is equal to the resistance. So resistivity is the resistance of wire whose length is 1 meter and whose area of cross section is also 1 square meter, and its unit is ohm meter. And in most of the cases, the resistance and conductance, they are parallelly used, because the conductance is just the opposite of resistance. So the reciprocal of resistance, we call it as conductance, and it is represented by the symbol K. And resistivity is and the reciprocal of resistivity is called as conductivity, which is denoted by the capital letter K. So this is the basic principle on which the electrical resistance tomographs have been developed. So my talk will be how these properties are affected by wood, and what are the parameters of wood that affects these electrical properties. So there are two sets of parameters that can affect the electrical behavior of a wood. The one is called the material parameters or material variables. And in case of wood, the material variables can be moisture content, species, density, grain orientation, and chemical constituents. So these are the main parameters which can affect the electrical properties of wood. And besides the material parameter, the experimental parameters, or we can call it external parameters, that can affect the electrical properties are the kind of electrodes that are used, then what are the pressure, contact pressure, then sample shape and dimensions, and then electrolytic effects, then magnitude and time duration of applied voltage. Anyhow, I'll not be dealing with the experimental variables, because as far as the ERT machines are concerned, most of the things have been standardized, like electrodes are fixed. And the experimental parameters I'll not be touching in this talk. I'll be just dealing with the material factors that can affect the electrical properties. So the first parameter is moisture content. Uh, wood, we know that it is a hygroscopic material. And if we look into the entire electrical properties of wood, it can be narrowed down to moisture content, because most of the other parameters, they get influenced by moisture content, and which in turn affects the electrical properties, either conductivity or resistance of wood. So before moving forward, we should know that wood is very hygroscopic because of its chemical nature. It contains cellulose, hemicellulose, and lignin, and these materials are made up of they have OH molecules in their structure. So because of that, they are hygroscopic. So they have a tendency to absorb moisture from the surrounding. At the same time, wood is a porous material, so the lumen can also absorb certain amount of water. So the moisture content of wood, uh, when a tree is alive, the moisture content, even it can range up to 200%. So now sometimes people may ask, if everything, if there is 200% moisture, then where is the wood available in that? So actually the calculation is bit different here. The moisture content, during moisture content calculation, we always take the initial moisture so the difference between the wet wood and the dry wood. Dry here we always go for oven dry wood, and we divide it with the oven dry wood. Because of that, because we are taking oven dry wood as the denominator, so the moisture content can even crosses 100%. This is an international convention, and everybody follows this principle. So the moisture content, as I mentioned, it can range to any from even 0% to even it can go to 200%, even sometimes more than that. So if we consider the entire moisture range, I think the moisture content above 30%, what we call around 25 to 30%, we call it as FSP zone. We call them as free water, because if you consider, I'll just give a small analogy of earthen pot. If you fill the earthen pot with lot of water and you keep it for a couple of days, so the wall also gets saturated. And so if you pour the water, whatever water is inside the earthen pot, it can be removed easily, but still the wall can contain certain quantity of water. So the water which was present in the inside the pot, we can consider this as a free water. So it can be removed easily, because it is not chemically bonded. It was just present inside the lumen, or maybe the vessel of the earthen pot. But the water which is present inside the cell wall, we can consider it as a bound water, and it is chemically bonded to the cell wall constituents, and that's why removing that water can be difficult. And in most of the cases, the bound water bound water content maximum can be around 25 to 30%. Until that range, we call them as fiber saturation point. And beyond FSP, the water will be available inside the lumen, and below FSP, it will be always within the cell wall material. So the moisture content, why I'm narrating this the principle of FSP, and because it has a lot of relevance with the electrical conductivity of wood. So if we see the electrical properties of wood, the dry wood is an excellent insulator. The resistivity of dry wood is in the order of 10 to the power 7 ohm centimeter at room temperature, and the resistivity decreases dramatically as the moisture content increases. So the left figure shows the resistance and the right figure shows the resistivity, how the both changes with respect to moisture content. So if I'll explain these two graphs, the decrease is exponential with increasing moisture content to approximately 10 to the power 11 ohm centimeter at 7% moisture content. If you see this graph up to 7% moisture content, the decrease in electrical resistivity is quite substantial. And if we consider, this is almost 5 times for each percentage increase in wood moisture content. And that means up to 7% moisture content. If we increase the moisture content from 0 to 7, for every percentage increase in the moisture content, the electrical resistivity can be increased by almost 5 times. But after 7%, the rate of decrease reduces, and it can go in 4 to 2 times until we reach FSP, fiber saturation point. And once beyond that, the decrease is becoming less pronounced with increasing moisture content. And if we see the beyond FSP, the relation becomes almost linear. If you take the logarithm scale, that is, if you plot the log of resistivity to the log of water, so it will be almost a straight line. So the resistivity drastically reduces as the moisture content of wood increases. In other words, the conductivity increases because they are both are reciprocal. So this is the figure that shows the resistivity of some woods. Actually, this was taken from a source called ACO in 1976. They have compared the resistivity of some wood species of Ghana and USA, as well as some bark, the resistivity of wood. The bark here, it is the inner bark. It is not the outer bark, the inner bark. So the resistivity of almost all the wood species are almost similar with minor differences. And the second important variable was wood density. And density is nothing but the mass by volume, or we call, sometimes we refer them as the specific gravity. So it is nothing but it indicates the amount of solid matter present in wood. And as in the previous lecture, it was mentioned that density is specific gravity is a very good surrogate or indicator of the strength properties of wood, and it can be easily measured. And there are different way of expressing density. Normally we represent density at 12% moisture content, or maybe at oven dry condition and green volume. So the depending on the quantity of moisture and the condition in which the densities are measured, so these parameters, the density values are reported accordingly. So it is reported that the density of wood, the electrical conductivity of wood increases with the wood density, and this curve says this shows the how the electrical resistivity. Here it is the conductivity, is not the resistivity, because I didn't find any relation graph for resistivity. So this K is the resistivity of entire conductivity of wood, and K dash is the conductivity of cell wall material, because the cell wall material density is higher than the entire wood. And rho here it is the density of entire wood, and rho dash is the density of cell wall material. So the conductivity, the ratio of this conductivity increases as the wood density increases. So this indicates that if the density of wood increases, the conductivity also can proportionately increase. But when you talk about sapwood and hardwood, um, there is not a huge difference in the wood density as far as sapwood and hardwoods are concerned. But the minor differences in the density can be accounted because of the extractives present in the wood. The third important variable that affects the electrical properties of wood is the structural orientation. And as far as wood is concerned, the structural orientation can be confined to the grain directions. So in a standing tree, the grains are oriented because there are three orthogonal directions, and the properties of wood are quite different in all these three directions. And this variation in property can be attributed to the orientation of the fibers, as well as the other anatomical parameters like race cells and vessels. So if we see the in a cross section, in a wood has three orthogonal directions. The vertical directions of a standing tree is called as longitudinal direction, because along that direction the fibers are oriented. And there are another perpendicular direction to the radial direction. So these two directions are although they we call them as across the grain, but they can be segregated into radial as well as tangential directions. So radial directions, this is parallel to the race cells, the orientation of race cells, because the race cells, they originate from the center and they migrate towards the periphery. So the direction that is parallel to the race cell direction, we call them a radial direction. And the direction that is perpendicular to the race cells, we call them as tangential directions. In the photographs, the tangential direction on the left side, it is perpendicular to the race cells, because there, as I told, the race starts from the center and it moves toward the periphery. So in these three directions, the electrical properties of wood are different.